Welcome to my talk on distribution awareness for AI system testing. My name is David Barrett and I'm from Nanyang Technological University, Singapore. Imagine you drive an autonomous car. The weather is normal. Normal conditions arise and the AI performs well. These situations are often encountered in the training data and therefore everything goes fine. A thunderstorm appears, which is considered an irregular condition, and the AI shows a low performance, may cause an accident, which needs to be avoided. So AI testing is performed to conduct many of these irregular situations so that we can identify the robustness of the AI system. But are all of these irregular situations relevant to the AI task? This is what we try to explore in this paper. Generally talking, AI testing is about generating data of diverse, irregular conditions to test the AI system robustness. Herefore, a seed is taken, mutated with brightness and contrast, given to the deep neural network, and then seen if it's predicted correctly or incorrectly. Then, coverage is measured to see how much of that new mutation stimulated the network at new areas to be considered new compared to the training data. The problem is, how can we know that this found error is actually relevant? Maybe it's very, very bright and therefore could not be seen in the real-life situation, as we can see at the bottom right. Therefore, we try to use out-of-distribution awareness, a technique where a score is used to identify if something is considered in distribution or out of distribution. Herefore, we use the training data as in distribution and build the overall OOD score distribution, where you can take the baseline, for example, from the softmax of your deep neural network. This is not very granular, so we explored other techniques too. We used 5, found the most granular one, and then seen how now OOD can help the AI testing. Looking at the results, things got very interesting. First, we trained other model architectures to truly find the ground cause, what causes an ID error and what causes an OOD error. 32.4% of ID errors could be fixed by changing the model architecture, while only 20.4% of OOD errors could be fixed. So therefore, OOD errors seem to be more data-driven, whereas ID errors seem to be more model-driven, confirming our hypothesis that OOD errors may not be relevant to the AI task. Then we looked at the AI testing frameworks, took 10,000 of their errors, and now looked how many of them are actually OOD. And the result was that 55.44% of these error cases were OOD and therefore may be irrelevant. So the state-of-the-art AI testing frameworks claim to find thousands of new errors, while more than half of them may be irrelevant to the AI system application. So what's the impact, we ask us as our final research question. Herefore, we built 2 buckets of data. One bucket with only ID errors, excluding those which we claim to be irrelevant. And another bucket which simulates the baseline, where all kinds of errors are inside. We retrained the network and then tested on a test set with mixed errors, which was usually done by other AI frameworks. Thereby, we were able to improve the performance, which we can now call robustness, by up to 10.05%. So therefore, we see that by including the OOD awareness in the AI testing, it can improve the robustness of the AI system, enabling it to generalize and be more reliant after deployment. As next steps, we already did in some new papers or are now pursuing to address OOD in the most helpful way along the AI lifecycle. When collecting data, we look at how OOD can guide the data selection to the most challenging yet relevant inputs. When testing, we look at how the test data is most diverse to resemble the application it will be used for. And when deployed, we can safeguard the input to make the user aware that now may be a situation where he needs to pay attention. Thank you very much.